This is an experience paper from Huawei company and Nanjing University about applying P4 language to round-2 competition architecture. I'm Zheng. Nice to meet you. I think many of you are familiar with P4, but I give a brief introduction here. P4 is a high-level network programming language. We define customized packet processing logic with P4 language and then compile the code into P4 programmable data plans such as Tofino, and then we build a new switch in completion time without having to understand the underlying hardware details. In this way, P4 makes network better. It accelerates the evolution of networks in many areas, such as in-network computing, congestion control, load balancing, and network management. On the other hand, researchers also make P4 better. Many efforts have been made to strengthen or expand P4, such as verification, scalable programming from foundation, and debugging tools. Although P4 plays an important role in hardware offloading and in testing new algorithms or protocols, there are some challenges of current P4 programmable network. The first challenge is the limited programmability. In P4 pipeline, each ML stage has limited cycles to process packets, and dependencies take up additional ML stages. However, the number of ML stages in existing P4 pipeline is limited, so the maximum logical length of a P4 program is limited. Another reason for the limited programmability is the restricted for memory operations. Suppose we need to implement a logic that stacks the minimal counter among several counters and updates the minimal counter. This logic is needed in a series of algorithms like conservative update counting sketch. However, the simple logic cannot be easily implemented in current P4 code. This is because when we figure out which counter is minimal, we cannot access the counter anymore because at this time, the packet and the counter are located in different ML stages. So the algorithms can be implemented by P4 are limited too. The second challenge is that the cessation of the next generation Tofino chip. The good news is that existing Tofino products are still selling and getting support, but we cannot see a new terabits per second level P4 programmable switch pretty soon. Based on both discussions, we are trying to introduce a new member, not a replacement of existing, to the P4 community with more flexible programmability and terabits per second level throughput. So let's take a look at the P4 programmable hardware architecture. The traditional P4 switch architecture is pipelined. Although the throughput is pretty high, the flexibility and memory capacity are limited. Another architecture is round-2 completion architecture. In this architecture, each core processes each incoming packet completely from start to finish before moving on to the next packet. Each packet is handled by a core independently and has unlimited logical length. It adopts many core parallel processing modules to scale the throughput to terabits per second level by using thousands of threads. And the round-2 completion architecture can equip a shared memory subsystem, includes on-chip SRAM for low latency forwarding, and off-chip high bandwidth memory or DRAM for large size flow tables and deep buffer. So P4RC is a framework that supports P4 language on Huawei's round-2 completion architecture chips. During the development, we overcome three main challenges. The first challenge is how to extend P4 language to fully leverage the flexibility of RTC architecture without alerting P416 core language. The second challenge is how to efficiently map P4 code to the round-2 completion architecture and allocate resources. The third challenge is how to verify the performance of the chip before loading P4 code in production environment. The performance verification is required because the round-2 completion architecture no longer has deterministic performance after completion, and it is possible to introduce poor performance code. Fourthly, I introduced the how to P4RTC extend the existing P4 language to fully leverage the round-to-completion architecture's flexibility. We introduced a new P4 architecture model, which are quite similar to previous one. Developers need to define parser, ingress, egress, and deparser control blocks. The main difference are that it uses parallel execution model, and the memory is shared among all processing units, such as tables and counters. Based on the new architecture model, we introduced many useful P4 extensions or externs for round-to-completion architecture. As for pipeline extensions, we introduced 2 pipeline rules in the new architecture module. The first pipeline rule is foreground pipeline. It runs common P4 packet processing logic. The second pipeline rule is background pipeline. It does not accept packets. It just runs an infinite loop of ingress control block and deparser. Background pipelines can generate customized packets by setting valid headers in ingress control block. Then the deparser emits these header fields to construct a complete packet. We also introduced some useful extensions for the control flow of the pipelines, such as for each, continue, break, sleep, and return. We also introduced some table type extensions. According to the deployment location, tables are classified into on-chip tables and off-chip tables. According to the memory layout and indexing mechanism, tables are classified into content addressing tables and linear addressing tables. The content addressing tables include exact matching table and the LPTM table, while the linear addressing tables are used to implement counters and registers. P4RTC uses annotation to define different tables. We also modify the paradigm of table operations. In traditional P4 pipeline, P4 table operations are performed in the control plane. The table operating instructions must experience long software stack latency and PCIe latency, so the control loop is long. In P4RTC, packets can operate table entries directly in the data plane, both for content addressing table and linear addressing tables. The in-data plane table operations reduce the control loop latency to the range of 100 nanoseconds to a few microseconds. Milliseconds. After finishing P4 coding, the completion phase needs to deploy P4 tables. In pipeline architecture, the compiler needs to meet the results constraints and the dependency constraints. In the round-to-completion architecture, the compiler also needs to meet results constraints of memory banks. Place the tables on the data plane according to their type, size, and capacity of memory banks. Besides, the compiler also needs to handle some performance constraints, as shown in the left diagram. Since tables are shared by many processors, the memory bank deployed with the whole tables often acts as a bottleneck, so we need to consider the performance issues when deploying tables. The optimization of table deployments are based on 2 basic strategies. The first strategy is table fragmentation. We can split a table into several shards and distribute the shards into multiple memory banks. In this way, we can accommodate tables that are too large for a bank and balance the load of the tables that are too heavy for a bank. The second strategy is table replication. We can replicate a table to multiple memory banks. In this way, we can balance the load of read-intensive tables to optimize performance. However, this strategy is known to impose this additional overhead on write requests. The compiler needs to automatically optimize the table placement during completion. We built an integer linear programming module to find a feasible and performance-optimized solution. The main objective of this module is to minimize the maximum memory bank load. During the development, we found that significant changes in traffic patterns may impact chip performance, as shown in the DAG figure, we use several tables to measure different kinds of flows. When the traffic pattern changed from TCP dominated to RDMA dominated, we found there is a significant performance degradation. We adopt a profile-guided optimization strategy here. When the traffic pattern has significant change for a specific amount of time, we will redeploy the tables according to the real-time table loads. Note that besides the table deployments, the compilation phase also needs to generate microcodes. Please see our paper for detail. After the compile generating execution, binary files, and the configuration, we can deploy the code to hardware targets. The run-to completion architecture does not have deterministic performance like in pipeline ASICs, so performance verification are required before deployment. We built a performance model that uses ESL methodology. The simulation process includes 4 parts. Firstly, we need to obtain a code path file based on the P4 programs and a specific workload. The code path file contains the probability of each microcode block being executed. Secondly, we generate traffic according to the code path. Thirdly, a cycle approximate chip simulator process packets according to the microcode embedded in the packets. Finally, the performance monitor measures and outputs the performance metrics such as latency and throughput. So in prototype P4 RTC on Huawei Nanjing 8000 FA1C routers with a 1.2 Tbps RTC chip with 8 GB high bandwidth memory. We use P4 RTC in several projects till now. And here I introduce one of them here. The project is to build an accurate per-flow traffic memory system with P4 RTC. As shown in the diagram, we use foreground pipeline to process application traffic and add flow entries directly in the data plane when the first packet of a flow comes. Then the subsequent packets of the flow can be measured. In the background pipeline, we use for each extern to iterate the table entries and report the flow records, which are already finished or timeout. We also introduce many optimizations on the measurement system with P4 RTC. Below, we summarize the key results of the measurement system. With the large memory capacity, the measurement system supports up to 50 million concurrent flows. It outputs highly aggregated measurement results in less than 0.5% of input. The output traffic includes complete flow records that contains flow keys, flow timestamps, and the protocol-related flow attributes. With the ability to directly add exacting matching table entries in the data plane, there is no hash clearance triggered eviction as it in existing works like TurboFlow. Thus, the traffic output volume is highly aggregated and compressed. Note there are some failed packets due to lock accretion during the insertion of flow entries. Since the table insertion time in the data plane is short and only occurs when creating flow entries, this type of package is minimal and can be handled by a dedicated CPU server. I conclude my presentation and our other contents in our paper in following 3 points. First, P4 RTC benefits P4 programmability. It incorporates P4 RTC architecture into P4 community, enabling functions that were previously unsupportable in P4. P4 RTC benefits RTC-based devices. It provides users with a simplified and general approach to developing functions in RTC chip. Finally, the performance module benefits P4 program profiling. It details the impact of different P4 codes on the chip on the specific traffic inputs. My presentation is over, and I'm happy to take some questions.